We are kind of running a little late here, but that's a fantastic talk. I'll bug you later with other questions that I have. So let's move on to the next talk. So our next speaker is Dr. Kimon Karras. He is a computer architect with AMD Networking Technologies Group. So they are starting off, I think Kimon finally mentioned that when he said somebody that AMD is in the networking business, like, oh, are you guys? So let's figure out what AMD is doing in the networking business. And without further ado, let me yield the floor to Kimon.
Thanks, Harry. Thanks. I'm Kimon.
Sorry.
No,
I apologize.
Yeah, no worries.
Yes, the Zoom thing. Yeah.
Sure. Awesome. So yeah, I'm Kimon. I'm with the NTSG, Networking Technologies and Support and Solutions Group, a new organization within AMD. As Harry said, AMD is not well known for its networking solutions compared to our competition, certainly, and that's for historical reasons. It has acquired networking know-how through acquisitions. One was the Pensando acquisition that happened last year, and one was the Xilinx acquisition, where I come from. And as you might know, Xilinx had acquired a UK company, SolarFlare, in 2019, and SolarFlare was and is a market leader in very low latency NICs, mostly for the financial space. And we're still very active in that area. It's a good market, and it's a good business for us, and AMD is looking to expand in that. It's I won't be talking too much about that line. It's though low latency is applicable to HPC, those products are also low bandwidth. There are 1025G products, and even that is actually overkill for the customers in that space. Their bandwidth requirements are usually around 1G and so on, but their latency needs to be ideally sub 100 nanoseconds. So therein lies the challenge. So a quick overview of the talk. I'll describe the motivation behind what we call our SmartNIC and DPU line. I'll introduce our portfolio, and then I'll provide a bit more details about our adaptive SmartNIC SoC and the AMD infrastructure accelerators, which are the DPUs that come from the Pensando line. And I'll give a couple of use cases in each case and show how they're architected and how they're programmed. So we are the problem is well known, and I think Gilead initially made the same argument. You know, the networking requirements are growing. You know, both with virtualization being extensively used in the data center, and multi-tenancy and so on, increased bandwidth requirements, security and whatnot. You know, doing all of that on the CPU takes up a lot of cycles, and these are cycles that are not used for doing application work. So ideally, we would like to offload that to a specialized module that could do that processing, right? And that has led to an evolution from a standard, very naive NIC implementation like the ones we had 20 years ago to a SmartNIC and then a DPU, which is what we have nowadays. So maybe what sets us apart from NVIDIA and Intel is that we also we have a multitude of solutions available, and we'd like to ideally combine them all in our solution, right? So we have ASIC-like fixed function logic, which is a standard NIC. We have embedded processor cores, which are even today ARM cores, and there's no immediate plan to change that. Let me put it like that. And but we also have FPGA fabric, which we integrate into our NIC solutions, right? And that's a legacy of the Xilinx days. And we're in each device, we're looking to find the correct balance between all of these components to achieve the best performance for our customers, obviously. So this kind of introduces the product line, which is what I mentioned before. We have these are the FinTech products, X2 and X3. X2 is a fully ASIC product, which has been around for I think 4 or 5 years now, but is still very successful. And X3 is a new product which is an evolution of X2 and also introduces FPGA fabric into that equation. So customers can build custom logic that implements their protocol processing. And then we have, as I said before, the adaptive SmartNIC, which is a product which came out of the Xilinx part of the Xilinx part of the business. It's essentially a hybrid between a custom network processing block, FPGA fabric, and a processing subsystem, so ARM cores. And we also have the DPU part of the line, which is the Pensando architecture, which is not dissimilar to the adaptive SmartNIC in some ways, as you'll see in the subsequent slides. And it's fairly complementary. It's more, it's higher latency than the adaptive SmartNIC, and lower throughput, but not low throughput. It still does 100, 200G and is programmable through P4, so it's very flexible. And on top of that, we have the Smart Switch, which is essentially a switch that leverages Pensando DPUs to offer smart switch functionality. So the adaptive SmartNIC, as I mentioned before, is our latest product from the Xilinx line. It's a data center solution, right? So it's intended to go into that environment. Is very high throughput. It's 400G and can sustain 400 gigabits per second line rate. It balances between very different heterogeneous designs, as I mentioned, an FPGA fabric and custom blocks and so on. It integrates PCIe Gen 5 by 16 and also CXL 2.0, along with DDR memories for local storage, and security also plays a big role there by incorporating the latest standards from the Open Compute project and PCIe security and so on, but also crypto offload engines inside the ASIC part of the chip. And this is kind of how we divide that workload. We have the ASIC logic doing DMA offload and the crypto pipes I mentioned, and network data plane offload. By that I mean initial reception of the packet, classification of the packet, and so on. And then we have the programmable logic, where we can do custom processing. We can add and remove network functions and so on, and that can all be done on the fly. The device doesn't have to be taken offline. It doesn't have to be connected to a JTAG cable, as you might have seen in the past or so on. That can be done while the system is deployed and running. And we then have embedded processing in the form of ARM cores, as I mentioned, where we do the network control plane, where we do telemetry and so on, and ensure coherency between the memory and whatnot. So in terms of performance, as I mentioned, there's the target is to do 400 megabits per second line rate, gigabits per second, sorry, or 400 megapackets per second in each direction. And we can also sustain that in all workloads. So we can do fully virtualized offload, and we can sustain line rate, and at the same time encrypt and decrypt packets as they come into the system. And on the left-hand side, you can see a bit how the system is put together on a very high level. So it essentially consists of a host subsystem and a network subsystem. And so packets go in and out from the network subsystem. And in the middle, you have the programmable logic, which you may use or you may not use. It's worth mentioning maybe that the card can be used as a standard NIC. There's no need to use the programmable logic if you don't want to. You can just use the ASIC part of the chip, right? And there's a processing subsystem, which is the ARM cores, and all of these are connected through a programmable network on chip, which allows for high bandwidth communication through all of these parts. And since this is destined for For a data center environment, we have given a lot of consideration into security. So we implement secure boot and key exchange and authentication, and we implement hardware firewalls on the SoC. So memory remains allocated to each application, and we cannot have spillovers into adjacent regions. And we also secure the data as it is in flight or at rest by encryption, as I said, which is integrated into the chip. So a couple of use cases where we use the chip, that could be either host attached or network attached or storage attached. And I'll show an example of each. So the first one is a very traditional application in the data center space, like it's it's OVS offload. OVS stands for Open Virtual Switch, which is what's used to translate one physical network interface card into multiple virtual interface cards, which you have for each virtual machine on the server. So all of that work is considerable work, and if you do all of that on the CPU, of course, that burdens the CPU. So what you can do on the adaptive SmartNIC is move all of that functionality into the SmartNIC, and then the CPU simply the VM on the CPU simply receives the traffic on the network interface, on the virtualized network interface, without understanding that this is essentially virtualized. And one can implement a lot of functionality there. We can implement extensive encapsulation and decapsulation, which is very common in data centers nowadays. Up to 4 layers can be supported at line rate. And we can also implement firewall offloads and so on to ensure safety and isolation between the various tenants. And the second use case is a host attached use case where you have a standard NIC functionality essentially. So this is the card connected to an Ethernet switch, and offloads are implemented on the card, and the card is connected through PCIe Gen 5 onto a host CPU. So this is a standard NIC offload, and this is similar, but it also attaches storage directly to the NIC. So the NIC has, I think, 32 PCIe Gen 5 lanes, as I mentioned. So this example showcases a hybrid deployment where you have both PCIe Gen 5 and two NVMe drives connected directly onto the NIC, whereas the subsequent design, the subsequent use case has more NVMe drives, but doesn't have a PCIe Gen 5 to a host because all the lanes are assigned to the disk drives. So this would be then a use case where you have a standalone offload, and you can implement offloads on the SmartNIC, like deduplication or data scrubbing or other offloads that are common in the storage space, right? So, and onto the Pensando accelerators, so the infrastructure accelerators or Pensando DPUs. The Pensando solution is a complete solution. It's not only a card, right? You see down below, I have here the actual accelerator, but there's a lot of stuff on top of that. There's the whole Pensando cloud software stack, which is essentially a host of solutions, both a host of solutions that allows you to use existing code to implement functionality. And you can see here that functionality is broken down into 3 domains: networking and security and storage. And there's also an SDK which allows you to create custom solutions for your use case. And I'll show a bit more about how that works later on. And so this is the Pensando line. The first chip Pensando that came out of Pensando was the Capri device, a 100G device. The current generation is Elba, which is a 200G device, and subsequently they've already announced that, or we've already announced that The next generation is going to be called Gilio, and subsequently Salina, which are higher performance and better memory. I'm not going to put numbers here. As you can imagine what those numbers would probably look like, right? But they want to make the announcement themselves. So I don't want to steal their their thunder in no way, right? But this is the line of DPUs, and this is their architecture. It's a busy slide. It's fundamentally not dissimilar to the adaptive SmartNIC architecture in the sense that there's a packet buffer in the middle, an SRAM packet buffer. This is the same as we have in the adaptive SmartNIC, and as the packets go in and out, they're stored there while processing happens in the data transform engines. And similarly, again, to what we have in the adaptive SmartNIC, here essentially there's a processing cluster per ingress or egress path and direction. So when here's the packet ingress, and there's a processing cluster here, and there's a processing cluster at the packet egress, and respectively on the DMA side to the host, there's a cluster, a processing cluster there, and for the transmission to the host, and one for the reception from the host. And all of this is interconnected by a NOC technology, and of course you have crypt offloads and the usual things you have in chips nowadays, DRAM interfaces and PCIe PHYs and so on. So in that regard, the architecture is similar, but it's also different in the sense that the MPUs are programmable processors. So essentially, each processing block here is a tiled architecture of programmable packet processing units with their own memory, their own cache, and their own TCAMs, and so on. So I mentioned before that the Pensando software stack allows for three types of solutions. It allows for turnkey solutions, things you can essentially take from the Pensando library and use as is. That will be, for example, NVMe over TCP and so on. That exists as an application, and you can use that without developing your own code. On the other end, there's custom logic. Logic in my head, coming from a hardware background, kind of means implementing gates. In that case, it doesn't mean that it's P4 software that has to be written. And in the middle, there's the Pensando SDK and library, and you can use that together with the existing applications to extend those and define custom functionality. And this is a bit more information about how that works. This is all done in P4. I'm not sure if everybody knows what P4 is. So it's a domain-specific language for packet processing. You'll see a plus sign there. The plus sign goes to custom extensions that have been introduced to the language to deal with the constructs which are not native in P4. The fundamental flaw in P4 is that currently it's stateless. So if you want to do stateful stuff, of which there's a lot in processing and in DMA transactions, DMA is actually implicitly stateful, then you have to add something on top of the existing language. So that's the plus sign here. It's custom extensions that compile to specific actions like those, the DMAs, engines, and so on. And those go to a compiler, and from that you go. You populate the tables and so on, and that goes then into the data center, the data plane path onto the logic. And together with the compiler infrastructure, we also provide a simulator, so you can simulate all of your code onto the simulator without actually even owning a card or deploying it on the card, right? So, and this is a simple example of NVMe virtualization. So similar to traffic virtualization, here we virtualize the whole NVMe traffic. So we actually run the entire NVMe TCP stack on the card, right? And that's a very complicated task, NVMe TCP. So the CPU doesn't need to care about that. So it's essentially a storage offload where the storage lies in the network, further out, and the data is brought into the AMD DPU over TCP and is unpacked here, recombined as needed, is reassembled, and then the storage block requested is handed over to the virtual machine without any intervention from the actual CPU on the host, right? So it's completely offloaded, and so yeah, and the DPU is available in a couple of form factors. So first of all, you have the DPU card, right? You can plug in a server. It's the typical model, and you have DPU appliances, and you have DPU smart switches. For instance, there's a switch from Aruba which uses a DPU, right? And all of these offer the same host of offload I mentioned before, and are programmable through the software stack I described. So, and just to summarize, AMD currently has essentially a new but considerable range of NIC solutions, mostly for the data center and financial space for historical reasons. As I said, and these are low latency NICs for the financial market. There are smart NICs which integrate FPGA functionality, and there's also the DPU accelerators, which are programmable via P4, and these essentially comprise our approach to network acceleration by integrating different heterogeneous components into one chip and allowing that functionality to be defined by software on top of that. So yeah, that's my talk. If you have any questions, I'll be happy to take them.
And again, since we are running significantly over time, probably we could take the questions offline. So I'll now yield the floor to Ron.
Yeah, let's get started with the panel.
Yeah.